All right, so we're gonna get started for today. Just so you know, homework 2 is due today. Lab 1 is due on Thursday. And after I cover the derivation part, I can answer questions if you have about Lab 1. And I also posted homework 3, which is due next Thursday. So for today, we're gonna finish discussing, discussion, but also just to derive this particular part. And we want to make sure that we know the posterior distribution for 1 over sigma squared, which is the precision parameter, will be a gamma. So if you start with a gamma, you're going to end with a gamma, and that's what we. Yeah. So if you start with a gamma with the for the 1 over sigma squared, you should arrive at another gamma, but then with a different shape parameter. So again, gamma has 2 parameters, and you start with alpha beta, and you end with alpha plus n over 2, and then beta plus the sum 1 over 2 of the sum of the square term of the difference. So last time I think I helped start it up of the derivation. So let me, I guess, maybe go back to that point, and I hope some of you attempted during the weekend maybe to see if you can see how to get the posterior. So again, it's being assuming that we're assuming that mu is given. So this is a gamma. So alpha beta. So that means the prior density is beta to the power of gamma, and then this gamma function of alpha, sorry, beta to the power of alpha, and then gamma alpha, and then 1 over sigma squared to the power of alpha minus 1, and then the exponent function negative beta times 1 over sigma squared. So that's what the prior is. The likelihood, we know it's a normal, IID normal, so we know that now we're going to express the likelihood function in terms of 1 over sigma squared, because that's the only unknown here. So you write capital L, and then we know that it's product of a bunch of IID normals. So we have 1 over 2 pi square root, and then square root squared in there. 1 over 2 sigma squared yi minus mu squared. Okay, and we further simplify it. I think we did last time. So this becomes 1 over square root of 2 pi to the power of n, and then we have to. And we have. So keep in mind that now we write everything in terms of 1 over sigma squared, because that's the thing that we want to recognize the terms about. Okay? So you keep writing that. So if that is the case, you're going to do this n to the power of, to the power of n over 2. Okay, so it started with 1 over square root of sigma squared. But now if we try to keep the term of 1 over sigma squared itself, then it raised to the power of n over 2. So that's why. And lastly, we have this form of negative 1 over 2, and then you can write 1 over sigma squared here. And then, I should say it should be a sum right here. Yeah, I think that's where we left with last time. And the goal is to try to derive the posterior. And so again, posterior, we write pi 1 over sigma squared given the data. And mu. So mu is given, so you always write it after the conditional sign. So we know that it's going to be proportional to pi 1 over sigma squared. That's the prior, and then the likelihood. Okay. So again, everything that is not about 1 over sigma squared is considered as constant. So you can throw them into the proportional sign. So let's spend a few minutes so you can work out the detail. You should come to the final posterior in this form. So it should be a gamma of alpha plus n over 2 and then beta plus 1 over 2 sum of yi minus mu squared. Okay. So again, in order to recognize this as a gamma distribution, you're going to match. So you see that I wrote it at the top over here. If you have a gamma alpha beta, that's what you see in terms of the random variable in the prior. So whenever you're trying to recognize the posterior, you should leave the form in that way as well. So you'll be able to recognize it. So let's spend a few more minutes here. I think last time we almost got to the point, but today we're going to spend some time here and then later move to lab 2. I will walk around to answer particular questions you might have in the derivation process. And I should also mention that I already posted the derivation notes on Moodle. So I mean, try not to look at it now so you can get the practice, but you can use that later for study. Now, just a clarification first that up here, all right, so this is just notation. This is the gamma distribution. You have this constant in front. It is beta to the power of alpha over, this is a gamma function. Okay, so we're writing this way, it's the capital version of this, and then it's alpha. So that's what that form is. So we know that whatever is a constant, so from the prior, the blue box gives us the constant from the prior, so we don't even need to worry about it. And then in terms of the likelihood, this is the constant, right? Right? Yeah. And then everything else is about 1 over sigma squared. So you can have those two terms. They are to the power of something of 1 over sigma squared. And these two terms is an exponent function. And they both have 1 over sigma squared multiplied within it, right? So that's how you should be completing, or I should say combining the terms. So if we combine the terms of 1 over sigma squared, it is alpha minus 1 plus n over 2. Okay? So you combine this and this. And then the other term is, so a good way to write it, as you see, is that, so the form of the gamma distribution is negative something times the random variable, right? That's what you see in the prior expression. So you can write 1 over sigma squared out, and then whatever you recognize after this in terms of multiplying with this term will be the second parameter for the gamma posterior distribution. So what you have is beta, and then plus 1 over 2. So beta is here, and then 1 over 2 with the sum of this will be the second term. Over here. Okay. Yeah, so once you come to this, we know that if you can recognize this in terms of a gamma, and we know that alpha plus n over 2 should be the first parameter, and beta plus 1 over 2 of the sum of all of the square term will be the second parameter for this gamma. Okay. Yeah, so this is the derivation process of recognizing this to be a gamma posterior distribution. And like I said, I think it's slightly easier than the other one that we did for the normal mean, because that requires completing the square and recognize it to be a normal posterior distribution. Okay, so but overall, for both of these cases, we first of all assume that one of the other parameter is fixed, right? We assume that it's given, so we only work with one parameter. So that's one. The second is in terms of the derivation techniques or tricks, it's really just recognizing what is constant and what is not. And then for those non-constant, you try to combine the terms in a way that you can recognize in this case the gamma, and then the other case is the normal. Okay? So make sure that you're getting a practice. Like, you can do this pretty efficiently and correctly, and that's pretty important as you see as we go along in the semester to see how to get the Bayesian methods analytically working. Okay, any particular questions here? Okay. All right. So if not, what's left for this part is last time I was saying if you have the final posterior distribution in this form, and then we know that if you know, say, those quantities, so alpha and beta, they come from the prior distribution. So you give a particular gamma prior, so you know the values of alpha and beta, and you know n is the sample size, right? And you know the sequence of y, which is from the data. And lastly, you know mu, because we assume that mu is known. So what this means is if you know this 5 quantities, you can know exactly what this gamma posterior distribution is. Okay, you know alpha plus n over 2, you also know the other term. And then from there, you are able to simulate draws for this 1 over sigma square in terms of its posterior distribution. The last time we saw that for the mean case, because then we know the mean the mean and standard deviation for the posterior probability of mu, and now we know. Yeah. Yeah, thank you. Yeah. So it's one of us. But, yeah. So anyway, where was I? Right. So you can then generate posterior draws of this gamma distribution, and then you can summarize it based on the draws that you have. But remember, in addition to generate like draws from this R gamma distribution, you can also use like P gamma, Q gamma, and D gamma, those kind of functions to return certain summaries of this known posterior distribution. Okay? So just as a demonstration, so this is the case that we assume that we're going with the beta 1, alpha 1, 1, gamma 1, 1, and then we assume that we know mu is 8. Okay, so mu is given in this case. So then what you can see is we define what beta and alpha values are. They're both 1. And then we can compute based on the formula that we saw, equation 16 of the posterior distribution. You can know the updated alpha and the updated beta from these 2 lines. And then lastly, you can generate a large number of them. So again, you can see that we use R gamma, and S is the number of draws that we're doing. And then you fit in the shape and the rate. So we call them shape and rate parameters. So just fit in the 2 that you computed, and then you'll be able to summarize, or like in this case, plot the posterior distribution for the draws of sigma. So this, again, we're going to see that once we get to lab 2 to do more practice. But overall, you can do this for sigma, and earlier we covered that you can do it for the mean as well. So keep that in mind, and it involves, so both of the 2 cases involves knowing the exact posterior distribution, and that's based on the derivation that we did. Okay. If it's not known, or we don't know what it is, that's going to be next unit of how to use certain computation techniques to achieve approximation to these distributions. Right now we know exactly what they are, so we can summarize them. All right.